Hello everyone, my name is Katerina Galitzca and I'm excited to kick off a new 6-part video tutorial series where I'll be exploring a powerful new simulation software tool called Nullspace. As a new user myself, I'll be learning the tool from scratch and sharing my journey with you. Nullspace is a next-generation 3D simulation platform that claims to solve electrically large problems significantly faster than traditional simulation tools and without sacrificing accuracy. So naturally, I had to try it myself and Nullspace provided me the license to do it. What caught my attention and got me really interested in that Nullspace has a very highly flexible Python API. It allows us users to set up advanced workflows like parameter optimization, uncertainty analysis, and generative designs. And sometimes it can be hard with our traditional simulation softwares. So I have experience in Ansys HFSS, CST, microwave office as antenna tool, and it will be very interesting for me to put Nullspace into test, and especially as an antenna engineer myself into antenna simulation tasks. In this tutorial series, I will focus on real-world antenna-specific examples. I will start with a simple single antenna element, bowtie element, then transforming it into antenna array. I will walk through importing of 3D models, for example, like step files of array DOM and so. And very interesting part for me is beamforming. We'll see how to set it up, how to get results, and what can be done here in Nullspace. And then, of course, we'll explore simulation of electrically large structures, right? So, for example, we will mount this antenna array that created before into a cellular tower. So my goal with this series is to first learn the software myself. As a new user, it's very interesting. I like to learn new things. And then I want to create just easy to follow tutorials that will help you understand what Nullspace can offer and what alternatives there is for existing simulation software. So let's get started. So as I said, we will create a bowtie antenna, a single antenna element in this tutorial. So as you can see, this is over-the-ground bowtie antenna that works at approximately 1 gigahertz. I was aiming for like lower frequencies, like cellular frequencies, around 1 gigahertz or so. This antenna is like bowtie type of antennas, I would say. Of course, not as simple as this one, but maybe more complex, but variations, right, of bowtie antennas. They are quite popular in cellular applications and in satellite applications as well. So I thought that this antenna can be good start. And then we will also, of course, make it complex by integrating the antenna array and integrating more things into it. So that will be interesting. But today we will just start with the simple antenna element. And this is how the user interface of Nullspace Prep looks like. So what Nullspace Prep is a software that helps you to prepare 3D model and mesh for your 3D model. And what was interesting for me, so like 3D user interface, as you can see, it's, well, I would say, quite similar to like all other like simulation software that we have, right? Of course, a lot of different things, and all simulation software, they are different. But you have like model creation. You can create bricks, for example, here, right? We can create brick. We can have width, height of the brick, like for the substrate, for example, or we can even write, as usual, write some like variables, for example, like sub W that I have here for width of my substrate. So this is normal, right? You can create with the user interface volumes, you have surfaces, and you assign materials. That's how it's done. But what's interesting is that you actually have several ways to set up models. So one way is to using the user interface, then another way is to using the journal. So the journal is written in kind of like simplified programming language, right? So here you can see that I set up all the parameters. So like my length of the arms of the dipole, port parameters, substrate parameters, and so on. And I created brick here with the width and height that I set up as a variable, and so then I can also move the substrate, and then I can create the port, like port structure here for like some support structure for the port, and then port itself, and then I can create curves for dipole arms. So here we have four curves, right? The segments of the curves, and then you cover it with the surface. So that's just very, very, very kind of interesting for me that you have this kind of history tree, right? That you also can change dynamically very, very easy. You don't need to do it in the 3D like user interface, right? Like going into the model of the like this brick, changing something. You can, for example, here I created the ground plane and it's 500 now, 500 millimeters. I use millimeters as units here. If I use it, if I change it right here in the journal and then I run it, now I have a smaller ground plane. But everything else is the same, right? The mesh, for example, settings are the same. So like the kind of like consistency of the journal is still there. It's just that I can change whatever line I want myself. Kind of remind me a bit about the history tree in CST, but much more flexible here. Like really, you can like use as a program language, right? And when you get a hand of it, if you understand like the program language of it, right? If you you can even write. You don't even use the interface, the user interface. And then of course there is Python API. So here even in journal you can translate into Python, and then you can just like write normal like Python in Python language and use it as well. Much more flexible as all Python users know. You can do a lot with Python. But I think this program, like this journal, is very easy, like very intuitive, even for those who kind of maybe not so close to programming, don't want maybe to use programming. I found it's very, very interesting that you can do it. So here in this, as I said, I set up the model, right? So the model setup, like easy, because it's very, very simple structure. We have a substrate with some width and height. We have our bowtie antenna structure. We have port structure. So with the port structure, I have some support here, some support structure to have the port in like one medium, right? So it doesn't have like several materials on the surface. So this is just how the ports should be assigned in Nullspace. And I create this like superstructure to rise it a bit. And then, yeah, that's basically it. We create the model. So let's see here. So this is the model it's created, right? And then what we need to do is that we need to assign the materials for our model. And that we do in Python. So we create library for our project. So as this antenna model is very simple, we only need substrate material, because perfect conductor material that I will use for ground plane and for antenna arms, it's already integrated in the program. So we only need to load, basically like assign the FR4 material that I will use for substrate. So here we like use the library that created by Nullspace, and then we assign material. So here is dielectric constant, and then tangent, and then we have also magnetic properties, but we don't have any for FR4. And that's basically it. We run it, and then our materials are integrated into the model, right? And then we can assign them. So here in this like 5-6 lines is basically material assignment that I've done. Is also very simple, like intuitive. You can understand what is done here. It's just you have load material library, and then you assigned for our substrate our material that we just created in material library, and then you assign the perfect conductor for ground plane and arms and so on. And then as well, one interesting thing is that you need to, of course, assign the excitation. You need to assign the port, and so how it's done in Nullspace is that you have like your port in two parts. You have one negative surface and one positive, and then you assign also impedance. So here I assigned 50 ohm, and basically here you can see in red my port like two parts, one negative, one positive. very fast. When you get kind of like a hand of it, you really understand how it's done, and you can like do it everything from this journal. It's very easy. And then of course we need to do mesh. So for doing mesh, I created some variable that like connected to wavelength, and we mesh port, and then we mesh our dipole arms here with a quite dense mesh, right? Like so we kind of approximately quarter of our mesh variable we use. Then we use the substrate. We mesh the substrate with the same kind of amount of mesh, because the substrate I chose in this project is quite thin, so 0.76 or something. So better to mesh, it's quite good, and so that we have at least one mesh kind of in the thickness of material. And yes, so we do the mesh, and then for ground plane we don't need such a dense mesh, so we mesh it quite loosely. That's basically all. That's all meshing that we need to do. We just need to kind of tell the program that this size mesh is assigned to this volume or these surfaces. Then we save it, and we're good to go. This is basically what is the Nullspace Prep is for, right? To create the mesh, to create the model. Everything else is done in Python. So we are moving to Python from that point when the model is done and the project file is saved. We go to simulation setup. So here we have our simulation object. We create simulation object, and we have some like a reference to our project file, right? And then we do the scale. So the default units for in Nullspace is meters, so I did everything in millimeters, so I converted in millimeters here. Then I set up my frequencies. I chose from 0.5 gigahertz to 1.5 gigahertz to run, because I expect my resonance to be around somewhere around 1 gigahertz. And then that's basically it. That's what we need to do for simulation setup. And then we also need to have a report, so to kind of get all our data from the simulation, right? And here we like what kind of like what frequencies I want to have in my far field points, right? So I have 11 points. I think it's quite good. You can have more, of course, and then you will have more smooth like plot for gain, for example. But then it also affects the simulation time, as always in every simulation software. And then we have some scanning angles, so normal, usual, and then we request far fields. And we save. So this setup, simulation setup, is very like short, right? Very easy, because our first example is quite easy, right? Single antenna element. We don't have a lot of things to get from here. Of course, it will get more complex the further we go with this design. But for now, it's quite intuitive, right? So after we run the simulation, so we just kind of run it and wait like minutes for it to simulate. We need to get our data, right? What we actually want to see. The simulator, the solver creates some files here for us, like a report and simulation, what we requested in the simulation setup, right? And we even can like look at it if you want. Like there is a lot of data, like what is happening, like what ports are excited. Of course, we only have one port here, but later we will have several ports in antenna array, and so what port is excited, what's happening with the mesh, and so if you are interested in this, you can also check. It's a lot of data here. You can scroll and scroll and scroll, and yes, so after we done with the simulation, we go to post-processing. And here we have our reference, our file, and then we create the object for our simulation, right? And for our simulation, we extract test parameters. So we get our like X parameters, then we translate them into dB, and then we also might be interested to look at the impedance, real imaginary parts of impedance, so we get that as well, and we plot them. That's like just straightforward. For those who use Python, it's very, very easy. You don't need to be very deep like a coder into that. And then we do post-processing as well, object for our far field report, right? So this is already from report for that 11 points that we specified in simulation. And here we have gain. also possible to get like directivity and so on, but I'm interested in gain. Then theta and phi, and so we get all this. Like I want to get some indexes, right? Because I know that, like for example, my cut for my antenna will be on like theta 90, and I want this point specified. Then I want bore side gain, some cuts here, right? For it, that I want to see like some copolar, cross polar, and so. And then I plot my gain, and then I plot the cut of the radiation pattern that I want to see. And then, of course, it's always interesting to get the radiation, like 3D radiation pattern. And that's basically is also not so long, right? Setup of post-processing. Of course, the more plots you have, the longer it will be. Like you can plot as much as you want here. But this, I think, it's quite like because this is just a single antenna element, so it's very like not so much things that you can actually like be interested in here. So here's our resonance, quite deep at well around 1 GHz as I was expecting, maybe a bit shifted. And then we have our impedance around 50 ohm. We have our gain, quite good gain here with like above 8 dB. Then we have our cut, and the shape is expected for over the ground antenna, right? We have like strong directivity in one direction. And we have our 3D radiation pattern, so it's always good to see how it looks from all the sides, right? So we don't miss anything. And yeah, so this is very kind of like straightforward setup of what to do with the single antenna element. And it will get more complex, but also more interesting as we go further with the beamforming, with antenna array, with the radome integration and so on. But I think that's in general, it's quite interesting to look at the new tool and to learn something new. So I will be waiting for you in the next part of this series when we will create the antenna array. And I hope that you found it interesting, and bye-bye.